Okay, hello everyone. Let's start this session by giving you some tips about homework 3, the last homework. I actually thought that was the simplest homework, but it turns out no. Okay, so there were basically two problems in homework 3. Let me open it. So this is assignments 3. So the first problem was about the difference between determined games and zero-sum games. And the idea was that I basically asked you to give me examples of games in all 4 categories here, or say that no such game exists. Some of you actually came up with proofs that some of these games don't exist. And that's quite weird because all of them exist. So all 4 combinations are possible. So all 4 combinations are possible. And the reason is basically because being determined and being zero-sum are not really as connected to each other as you might think. So the way you should probably think about this is that zero-sumness basically talks about what happens in every play of the game, in every infinite path in your game. So the game is zero-sum if every infinite path either belongs to the objective of player 1 or to the objective of player 2, but not both, right? But when we're talking about determined games, we are talking about strategies. Basically, a game is determined if from every starting point, from every vertex of the game graph, either player 1 has a winning strategy or player 2 has a winning strategy. And we also defined what winning strategies are. So a strategy for a player is a winning strategy if no matter how the other player plays, the outcome is part of the objective of the player that wants to win. Okay, so based on that, looking at these 4 cases, everyone could get 2 of them at least. So everyone got determined zero-sum games, which are all the examples that we have in the course. And almost everyone got non-determined non-zero-sum games as well. So in order to get a non-determined non-zero-sum game, you can just do something really crazy, like define any random objectives for the 2 players, and it's likely that you will get a non-determined non-zero-sum game. But the cases that were actually confusing to people were these 2. So one case is determined non-zero, and the other case is non-determined zero-sum. Okay, so first of all, I'm not going to give you final answers here. I'm just going to give you some tips about how to create such games, because of course you can resubmit the homeworks. So in case of determined non-zero sum, what does non-zero sum mean? It means that in some cases, even after you have the outcome of the game, even after you have the infinite play, you cannot tell which side wins. So you can basically think of games that have ties. All the games that have any sort of tie in them are non-zero sum. And now you want the game to also be determined. So from every starting point, you want one of the players, at least one of the players, to have a winning strategy, right? So try to come up with a game in which we have ties, but whenever a player has a winning strategy, he actually has a strategy that avoids these ties. Okay? So if you come up with such a game, it would be determined and it would also be non-zero sum. But the hardest case is actually the case of non-determined zero sum. And I think I read more than 10 proofs that this is impossible. And really good job. At least check your proofs. So let's talk about non-determined zero sum. What does this mean? This basically means that for any given outcome of the game, because the game is zero sum, you have a unique winner, right? But it's also non-determined. So in order for a game to be non-determined, it's enough for it to be non-determined from a single vertex. So let's just fix some vertex V, and let's say that we want to make the game non-determined at V. What does it mean that the game is non-determined, especially now that it's zero sum? It means that for every strategy sigma 1 of player 1, there is a strategy sigma 2 of player 2 such that the outcome is a win for player 2. right? So no matter what player one does, player two has a way of spoiling it. And you should also have it on the other hand. So no matter what player two does, for every strategy sigma prime two of player two, there is a strategy sigma prime one of player one such that spoils it, and then the outcome is a win for player one, right? And it's actually important to be very careful about the quantifiers here. So in the first sentence, I'm saying for every strategy sigma one of player one, there is a strategy sigma two of player two. So sigma two can depend on sigma one, right? And then here I'm also saying for every strategy sigma prime two, there exists a sigma prime one. So sigma prime one can depend on sigma prime two. Okay. So the way you can think about this to get more intuition is that, let's say you are player two and player one has told you what his strategy is going to be throughout the game. So player one gave you his entire strategy, the whole function that maps histories to next moves that he wants to make. And based on this, you want to make a strategy for yourself. And on the other hand, it's also similar. Okay. But one other tip that actually helps here is that, well, when you are, what you have to do in this exercise is to just come up with an example of a game that is like this, right? And what that means is that you have to come up with an arena with objectives for the two players, and that's it. And then just prove that these things hold.
Should we specify them too, or is it enough that we just keep the graph of the game?
As long as you can prove that it's non-determined and zero sum.
No, I mean, should we specify each detail or just the graph is enough?
Well, as long as it's convincing. I mean, I don't want you to, especially if you're coming up with a large graph, I don't want you to draw all of it. But here's the thing. So when you are doing this, when you are designing the arena and the outcomes, you can actually do this thinking about the strategies. So here's another tip. Create a game such that the outcome starting at a given vertex V is different whenever someone changes their strategy. So I want this function, outcome of V sigma 1, sigma 2, to basically be 1-to-1, right? So whenever one of the players or both of them even make the smallest change in their strategy, we want the outcome to be different. It's actually not hard to come up with games that are like this, but just try working on that. Okay, and now that the outcome is different for every pair of strategies, what was an objective? An objective is basically just a set of outcomes, right? So you can just handpick. You can say for this strategy and this strategy, I want player one to win. For this other combination, I want player two to win. And just do this handpicking in a way that it makes the game non-determined. So handpick the outcomes that you want to be in the objective of each player in a way that this thing is satisfied. So for every strategy of player one, there is a spoiling strategy of player two. For every strategy of player two, there is a spoiling strategy of player one. So that's it basically. And another point that I should say here is that don't try to come up with classical objectives here. Classical objectives are always determined and zero sum. So you will not get non-determined classical objectives or any combination of them.
What do you mean by classical objectives?
So reachability, bookie, safety, parity, and any combination, any normal combination of these things. Okay. So this was about exercise 1, but let's also talk a little bit about exercise 2. So this one was also confusing for a lot of people. So here we have basically a 2-player infinite duration game on graphs. And now instead of just having one target set, player 1 has 2 different target sets. There is T1 and T2. And the objective of player 1 is to visit each one of these 2 sets infinitely many times. Okay. And I'm also saying that the game is zero sum. Okay, what does it mean that the game is zero sum? It means that the objective of player 2 is to force the game to visit either T1 or T2 only finitely many times, while the objective of player 1 is to visit both of them infinitely many times. Okay. Now, here are some of the, well, actually one of them was common, but here are two of the problems.
Sorry, can you also consider the case that player wants the game to not visit bookie T1 and bookie T2?
I don't understand what it means to visit bookie T1.
Actually, to, I mean, get bookie T1 or bookie T2. Because you said,
yeah, that's also correct. Yes. So player 2 wants to either make sure that we have co-bookie in the complement of T1 or co-bookie in the complement of T2. Yes. Okay, so let's just formalize this a little bit. So the objective of player 1 is basically this. It's bookie T1 intersection with bookie T2. And so bookie T1 was the set of paths that visit T1 infinitely many times. Bookie T2 was the set of paths that visit T2 infinitely many times. And I just realized that we don't. So objective of player 1 is to be in both of these two sets. So he wants a single path that visits T1 infinitely many times and also visits T2 infinitely many times. And this is very important. A lot of people just computed the winning set for bookie of T1 and the winning set for bookie of T2 and just took their intersection. That doesn't work. Why doesn't it work? Well, basically, if you are in the winning set for bookie of T1, this means that you have a strategy that ensures the game visits T1 infinitely many times. And if you are here, it means you have a strategy that ensures the game visits T2 infinitely many times. But it doesn't mean that these strategies can actually combine, right? And here's an example. So consider this simple game where everything is just under the control of player 1. And let's say that T1 is vertex 1, T2 is vertex 2. So starting from either 0 or 1, player 1 can ensure that he sees 1 infinitely many times, and the same thing happens in 0 and 2. But there is no strategy for him to visit both of them infinitely many times. So basically, this does not hold. You can't do that. And another thing that some people did, this was less common, but I have to also mention this, is that bookie of T1 intersection bookie of T2 is not bookie of T1 intersection T2. These two are different. So what the first one says is that I want to visit T1 infinitely many times, and I also want to visit T2 infinitely many times. What the second one says is that I want to visit the intersection of T1 and T2 infinitely many times. So you can have a path that comes here, visits T1, goes out, visits T2, comes back, visits T1 again, visits T2 again, so on, without ever visiting their intersection, right? This path would be in bookie of T1, intersection with bookie of T2, but it will not be in bookie of T1, intersection T2. So these are two completely different things. And actually for this exercise, I would say, go back to the lecture and look at how we found the complements of deterministic bookie automata. And that's going to give you some ideas about what kind of construction you can have here. And generally speaking, you have to also change the arena. You can't just keep the arena the same and do something with the objectives. Okay, so after that quite long tip session, let's go on and actually continue with our work on automata on infinite words. Okay, what did we see in the previous sessions? So we defined several different types of automata. Today we will define another type. And we saw that the languages of deterministic Boole automata are closed under union and intersection, but not under complementation. This was the notorious example of the language of all strings that have finitely many zeros. And then we also saw that non-deterministic Boole automata are strictly more expressive than deterministic case. And the thing that actually took most of the previous session was Boole's construction for complementation. We showed that languages of non-deterministic Boole automata or omega regular languages are closed under complementation as well as union and intersection. Well, actually, we haven't seen intersection yet because, again, intersection is this example. But you will all solve it, hopefully, now. Then we talked about some of the classical problems. We talked about emptiness. We saw that deciding whether a Boole automaton has an empty language is actually quite easy. You can always do it in linear time, even if you have non-determinism. Then we talked about universality, which was, in a sense, the opposite of emptiness, whether everything is in the language, whether everything is accepted. And there we saw that the problem is easy for deterministic case when we had a linear time algorithm, but it was hard for non-deterministic Boole automata. And last session, we actually saw a proof of, okay, not NP complete, but NP hardness of non-universality. Then we talked about complementation. Because of this NP hardness that we had in universality, we also have NP hardness for complementation, but we saw some complementation by Boole. And in 2 sessions ago, we had already seen how we do complementation for deterministic Boole. And finally, I told you that another problem that is very important is the problem of containment. And the idea here is that you are given 2 automata and you want to see whether the language of one is included in the language of the other. And actually, we're not going to talk about containment a lot. We're only going to use it in the later modules. So the way we solve this is that the language of A is inside the language of B if and only if it has no intersection with the complement of the language of B. So if you can do complementation and you can do intersection, and if you can also do emptiness checking, then you can do containment. Okay. So now in this session, we're going to talk about a completely different problem, and this is the problem of determinization. So the idea is, again, very simple. You have some automaton A, and your automaton is non-deterministic. Now, you don't like non-determinism. You want to find another automaton B with the same language, but you want this automaton B to be deterministic. Okay? So I'm sure you have already seen examples of this in case of finite automata. So if you have a non-deterministic finite automaton, you can always do that classical subset construction and make it deterministic. It increases the size of the automaton, but that's fine. Based on the things that we have seen until this point, we also know that it's not possible to get a non-deterministic Boole automaton and determinize it into a deterministic Boole automaton. And this is, again, because of that notorious language that was realizable here, but not here. So if we want to do determinization, we have to make sure that our automata are at least expressive enough, that they can really express any language that could be expressed by the non-deterministic automata. Okay, so this tells us that deterministic Boole automata are not really interesting in any sense. So what can we do? We can look into other types of deterministic automaton. For example, we can look into deterministic parity. Or we can look into what's called deterministic Rabin automata, which is what I'm going to do in this session. And so in this session, I'm going to basically define the notion of Rabin automata, and then I'm going to tell you about a very classical algorithm, probably the most classical algorithm in all of this field, which is Safra's determinization. And I took all of the course notes and figures for this session from this link. So this is from, I think, the University of Bremen. Okay, so let's start with the definition. What is a Rabin automaton? A Rabin automaton is an automaton on infinite words. So it has all the parts that you would expect, just like all the other automata that we have seen. And the only difference is in the accepting condition. So I'm only going to define the Rabin accepting condition. So in a Rabin automata, the accepting condition is a bunch of pairs of sets of states. So my accepting condition is E1, F1, E2, F2 until EK, Fk. And each one of these are subsets of my set of states Q. So E1 is a subset of Q, F1 is a subset of Q, so on. So we have K pairs of subsets of our states, and these are the representation of our acceptance condition. And we usually say this is an automaton of index K, meaning that we have K different pairs. Now, when is a run accepted? A run is accepted if there is one of these pairs. So if there is one I, such that EI is visited only finitely many times, but FI is visited infinitely many times. So you can think of it like the sets on the left, the EIs are undesirable, and the sets on the right, the FIs are desirable. We want to make sure that there is at least one index where we visit the undesirable ones only finitely many times, but we see the desirable ones infinitely many times. Okay, so consider this automaton here, and let's ask some questions. So, oh, I just realized that I haven't opened the chat box. Oh, okay, there are no messages there, so that's fine. Okay, so consider this automaton, and let's look at different accepting conditions, different Rabin accepting conditions, and see what languages they give us. So what happens if my accepting condition is this? And I know that the brackets seem kind of crazy, but basically the acceptance condition is a set of pairs of sets. Right, so this is why we have these brackets here. So in the first case, I have only one pair, and the pair is Q1, Q0. So I want to accept all the strings that visit Q1 finitely many times, but visit Q0 infinitely many times. What strings would those be? Can you give me the language? Right. It's if we have finitely many Bs. Because if we have finitely many Bs, at some point we come to Q0 and then stay there. Right. But if we have infinitely many Bs, we will see Q1 infinitely many times. So already with this example, we know that deterministic Rabin automata are much more expressive than deterministic Buki automata, right? Because this was a language that we could not model in deterministic Buki automata, finitely many Bs, but we have it here. Okay. And what happens if we swap the two? What happens if my pair is Q0, Q1? So I want to visit Q0 finitely many times, but Q1 infinitely many times. And this is just the same thing. It's finitely many A's, right? Okay. Now, what happens if I just take the two of these and use them as two different pairs? So let's say my accepting condition is this. I would accept either if I visit Q1 finitely many times and Q0 infinitely often, or if I visit Q0 finitely many times and Q1 infinitely often. So because we have only these two states, we have to visit one of them infinitely often, right? But this is not the set of all strings. Why? Because it excludes the strings that visit both of these infinitely many times. right? But at the same time, this is actually the union of the two previous cases that we saw. So taking union in Rabin automata is extremely easy. You just put the pairs together. Just take the union of the accepting conditions, right? Okay, of course, this is assuming that we are on the same graph structure. Otherwise, the union is not that easy. Finally, what happens if my pair is this, empty set and Q1? So I want to visit the empty set finitely many times, which always happens. And I also want to visit Q1 infinitely often. So I basically just want to visit Q1 infinitely often. And this is the Buki condition. So this is actually yes. Buki is a special case of Rabin. And how? You just put your Buki set in place of this Q1 here, and you let the left set be empty, right? Because the empty set is always visited finitely many times. And there is no way to visit the empty set. It's always visited 0 times. So you can just use this to model Buki. And you can model co-Buki very similarly, right? So you just put it on the left-hand side and you ignore the right. Okay, so now let's get into the actual meat of the session. Let's talk about determinizing non-deterministic Buki automata. Again, let's just go back to the basics and look at the finite case. So in the finite case, if we had some non-deterministic automaton A, and we wanted to determinize it, what would we do? We would just create states that correspond to sets of states in the original automaton, right? And then we would just follow the transitions of the original automaton. So, for example, from a state that is Q0 and Q1, if I see A, I just look at my original automaton. I see that with Q0A, I can go back to Q0. With Q1A, I cannot go anywhere. So if I'm in one of the states in Q0 and Q1, and I take one step with A, I know that I'm in one of the states here, which is just Q0. And this worked very well for finite automata. And the reason was that basically in finite automaton, the only thing that we care about is where a path ends. So as long as you keep track of the endings of all the paths that you have in your non-deterministic version, so your deterministic version is just keeping track of the ends of the paths, that's enough information for us, right? But why doesn't this work for Buki automata? Well, the simple answer is because we don't just care about what happens at the end of a path, because we don't have an end of a path. What we care is actually what happens during the path. And we care which vertices are visited infinitely many times, right? So we can actually come up very easily with a counterexample showing that this kind of construction doesn't work for Buki. And this is also easy. So just take this example here, which accepts what languages? So what is the language of A? It accepts which strings as a Buki automaton? So it's the set of strings that have finitely many ends, right? Because it can go here for a finite amount of time, and then it has to commit to seeing only Bs. So if we do this construction, basically the subset construction that we had in the finite case, then you can easily see that there is a cycle here, right? So you can just cycle BA, BA, BA. And that's bad. Why? Because, well, BA, BA, BA has infinitely many A's. And it wasn't accepted originally, but it's now accepted here. Why does this happen? Because, well, you start here, which is the right starting point, and you take the edge B. In the right side, you go to this state, but what happened in the left side was that you would be in Q1, right? But then when you take the edge A, what happens? If you take A from Q0, you can stay in Q0. But if you take A from Q1, you should reject. There is no edge A from Q1. But here, what happens is that you're just taking the union of all possibilities. And the union of all possibilities is going to Q0. So even though you cannot go from Q1 to Q0 using this edge A, you can actually, in this subset construction, go from this subset to this subset. And that's what's really breaking everything. So you see, basically, the point here is that even when I'm in this state, when I know that I'm somewhere either in Q0 or Q1 in the original automata, it actually matters which one I am in. And it also matters how I got here. How many times have I seen accepting states? So we need a lot of more information, and we have to actually change our accepting condition in B to something other than bookie. So let's say that I give you some run of this automaton B, which is created in this naive way. And I want you to tell me when I should accept this run so that the language becomes the same as the language of A. Well, here's one way of thinking about it. And this is actually the intuition behind Safra's construction that I'm going to go through today. So let's say that I have two sets of states, X and Y. I write this X, U, Y, and I usually read this as U projects X into Y, or X covers Y through U. Okay? And when I write this, what I mean is that for every state in Y, for every state Q in Y, there is some other state in X, such that I can start from that state in X and using a path that is a run that conforms with the word U, get to the state in Y, right? So for every Q in Y, there is a Q prime in X, such that there is a run from Q prime using this word U that reaches Q. And additionally, I also want this run to visit one of the target states, one of the bookie states somewhere in it. So it can visit it at Q prime, or anywhere in between. So when I write this, this basically means that if you give me the automaton in a case where I know that we are in one of the states in X, I can be in any of the states in X. So this is the same construction as here. Then if we take the word U, then we are sure that we can be in any of the states in Y, right? It's actually very important that you understand this definition. It's actually, you have to look at it from the point of view of Y. So for every state in Y, there is a way of getting here from somewhere in X, right? It's not the other way around. So if you, there might be states in X such that you start there and you run U and you never reach Y. That's fine. What I really care about is that for every state in Y, there should be a state in X and a run using the word U that gets me to that state in Y. Okay? Now, let's say that I have an infinite run of my non-deterministic automaton A. And let's call this run A1, A2, so on. And now let's take the corresponding run of the automaton B, which is now determinized using this subset construction. So there is only one run in the automaton B, and the run is basically a sequence of subsets of states of A. So there's S1, S2, so on. So I call the run in A, A1, A2, blah, blah, and the run here is called S1, S2, and so on. Okay. So if in this run, in the run of the deterministic automaton, I can find infinitely many places where I can chop the run. So at indices ij, I can basically chop the run such that I have this. Basically, Si1 covers Si2, Si2 covers Si3, and so on. And they actually cover each other using the words that appear in the indices between them. So Si1 covers Si2 using the word between indices I1 and I2. Si2 covers Si3 using the word between indices I2 and I3, and so on. What I'm claiming is that if I have such a way of chopping down my infinite run, then I should definitely accept. Now, why? Okay. So, and I should have probably, sorry, I forgot to put the initial state here. So there is also that from the initial state, so the initial state is Q0, I should be able to get to the first one of these. So if I have such a sequence, and these SIIs are basically subsequences of my run, right? What does this mean? It means that for every vertex that is in Si1, there was an initial vertex such that I could run this part of the word and get to this vertex in Si1, right? And then the same thing goes on for Si2. So for every vertex in Si2, there is a vertex in Si1 such that I can run this part of the word and get from that vertex to Si2. So putting these two together, there is definitely an initial vertex that reaches Si2. And also another important point here was that in each one of these reachabilities, we were also seeing a Bookey state throughout the way, right? So somewhere in the way, I'm seeing a Bookey state. So what I can be sure of is that whenever I reach a state in Si1, I have visited my Bookey states at least once. And when I continue, whenever I reach a state in Si2, I have visited my Bookey states at least twice. And this goes on and on. And actually, you can easily prove that this gives you a path in the original automaton that visits the Bookey states infinitely many times, right? So based on that, and actually you can show that this infinite run, if it's accepting, it would be part of this. This is exactly the example that you're looking at. So based on that, if I can take my run of this deterministic automaton that I achieved by subset construction and chop it down into several different parts so that I have these coverings, then I should accept. But actually, I can say something much stronger than this. So every time that I'm working in this subset construction, I'm basically keeping track of which vertices can be the endpoints of the path until now, right? So when I go I steps, what I'm keeping track of is that which one of the states of my original automaton could be reached after these I steps on this word. Now, what happens if I don't have great memory and I just forget some of these? So let's say that I'm at step I have a bunch of vertices. I have 10 vertices that I know I could be here. And I just say, okay, I want to get rid of 5 of them and forget them. This also gives me a run, not exactly a run, but a sequence. So I can get a sequence S'1, S'2, so on. And all of them are subsets of S1, S2. So this is a sequence such that every element is a subset of the corresponding element in the run. And if I can do this chopping on this sequence then the same thing that I said before also holds. So basically, all I'm saying here is that you can forget some of the vertices that you're at. You can forget some information, and if you forget this information and still make it, still reach Pookie, that's fine. Okay. So this is our main idea for trying to prove and trying to basically reduce from the non-deterministic case to the deterministic case. Okay, but now let's become much more formal. So let's say that I'm given a non-deterministic Pookie automaton, and I want to create a deterministic Rabin automaton that accepts the exact same language. So we saw what kind of information we have to save. And there is actually a structure called a Safra tree, which is named after the person who first came up with it, Safra, that saves all this necessary information. Okay, so what is a Safra tree? Let me give you a complete definition first. It might sound weird, but then when we continue with it and do our proofs, you see that it's kind of basically the same intuition as here. Okay, so let's say that I have a set of numbers, and for this construction, I need twice as many numbers as my number of states in the original non-deterministic Pookie automaton. So let's say that my set V is just a bunch of numbers, 1, 2, 3 to 2Q. We will see this later on as we create this. So I don't actually use it that much. So you can, instead of this, you can just think that V is a set of consecutive integers. The only thing that I care about V at this point is that V is a finite set of numbers. Okay. So I define a Safra tree, and a Safra tree is basically a tree, and every node of this tree is numbered using one of these numbers that I had in V. So V is the set of vertices of my tree. Not exactly the set of vertices of my tree, but a superset of set of vertices of my tree. So for some of these numbers, I have a vertex in my tree. For example, here I have a vertex 1, vertex 2, vertex 3. So you can think of V as the numbers that I use to number my vertices in the tree. Okay. And also in this tree, the children of each node are ordered. And what I mean by that is that there is a left child, middle child, right child, so on. This is not actually a binary tree always, but the order of the children is important. So you cannot just swap 2 and 3, and that wouldn't be the same tree. It's a different Safra tree, okay? And then other than this, each node in this tree is also labeled with some subset of our states in the original automaton. So for example, here, node 1 is labeled with Q0 to Q4, and node 3 is only labeled with Q2. So every node of this tree corresponds to a subset of states of the original automaton. Now we have some constraints on these labels. And the constraints are basically siblings have disjoint labels. So you can see that the label here, Q0, Q3, Q4, does not intersect the label here, which is Q2. So siblings should have disjoint labels. And also the label of each node should be a strict superset of the labels of all of its children. So if a state appears in 2 or 3, it should also appear in 1. But also 1 should have at least one state that doesn't appear in any of its children. It should be a strict superset. Okay. And finally, just to make things even more strange, some nodes are marked by some marker. And for marker, I'm here just using this. Okay. So this is what we mean when we say a Safra tree. Yes, so that's exactly what I'm going to cover now. Yeah. So basically, the idea of a Safra tree is that we have to determinize our non-deterministic Booki automata. So we have to keep track of all the possible runs of the non-deterministic Booki automaton. We have to save some information. And we saw that it's not enough to save which vertices can be the endpoints until this point. We actually need to save some more. And very roughly, not exactly, the intuition is that, so these are all the vertices that can be the endpoints until this point of the run. These are all put in the root of the tree. And these are vertices that we can reach, but we can also see a target vertex at least once before reaching them. These are also very similar. But why we have this distinction of different children, you will see in a moment. Basically, the idea is that they saw the target state at different points. So you can think of this as I can reach these vertices up until this point of the run, and I can reach these vertices while having seen some target state, and I can reach these vertices while having seen some target state, but in another time, not the same time as this one. But then there is a lot of more details in there. So the intuition is not exact. The thing that is exact is the definition. Okay. So how do we determinize? So let's say that I have a non-deterministic Booki automaton A, and it has all the parts that you would expect. So it has an alphabet, a set of states, a set of initial states, a transition function, and a set of target states, which are the Booki states. I create a deterministic Rabin automaton B. And here my set of states in B is the set of all possible Safra trees over A. So any tree that satisfies these conditions, I have a state for it. It's a really huge set, of course. But I have this set, the set of all Safra trees over A. And basically, I use each one of these trees as one state. The way you can think about this is that in the finite case, we had to keep track of a subset of states of the original one and call it a state of the new automaton. But now we have to think about a Safra tree of states of the original non-deterministic Booki automaton and think of it as a single state of our deterministic Rabin automaton. Okay, so because it's a deterministic automaton, it has to have a single starting state. And the single initial state is this, basically, this tree. It's a single node tree, only one root. The root is numbered 1. And the set of vertices in the label of the root are the initial vertices of the original non-deterministic Booki automaton. And this still matches our intuition, right? Because at step 0 of execution, we can only be at the initial vertices, and we cannot have seen any targets. Okay, now let's talk about transitions. So this is a deterministic automaton. So my transitions would take a state, which is now a Safra tree, and also a letter of my alphabet, and they will give me a unique successor state, a unique Safra tree. And this is the process for creating it. So I'm going to go through the process, then give you an example. And this all makes sense when you see the proof, but before that, it might not make much sense. So here's how we do it. So let's say that at the moment I am at a Safra tree S, and let's say that I read the letter A. So what other tree do I want to go to? So I start with my tree S, and I make some changes until I get the tree that is my next state, right? The first change that I do is that I remove all these marks. I remove all the exclamation marks. The second change that I do is that if I have a node in my tree and the label of this node intersects my target set, then I create a new child for this node and put all the vertices that were in this label and also the target set in that child. So this is the same idea that I was here. I looked into them and saw that, for example, Q2 is a target vertex. So Q2 is now different from all the other vertices that I can be in. Why? Because the path to Q2 actually saw a target and the path to the other ones has not seen a target yet. So the way I model this is that I create a new child and I put Q2 in that child. If there were several vertices like this, I would put all of them in that child. Okay. And we put this child to the right of all other children, because remember that we had this ordering on our vertices, and so the order matters, and we put it to the right of all of its siblings. Okay, this is step 2. Then what I do is that I actually do the steps. So this is again similar to the finite case. Here, if I'm in Q2, I just go back and look into my original automaton and see where I can go from Q2 using the current letter. And I just update this subset. And I do this in every node of my tree. So in every node of my tree, I just replace all the states that are in that node with their successors using the current letter. Okay. Now I have to also do some other works on my tree because I have to make sure that these conditions are satisfied. So the first thing that I do is what's usually called horizontal merging. And it says that if there is some state that appears in some vertex of the tree, but it also appears in a sibling to its left, then you can remove the rightmost one. You can only keep the appearance in the left. So this is what's called horizontal merging. So if I have a node U and I have a state of the original automaton Q, and if Q is in U, and if there is also another sibling V of U, well, to its left, sorry, okay, that is to the left of U and also contains the same state, then I can remove this state from U. And actually, and also from all descendants of U. The next step is very simple. If I have an empty node, I just get rid of it. We don't really care about empty nodes here. If you have an empty node, remove it. And finally, remember this condition here. We wanted the label of each node to be a strict superset of the union of its children. And if this is not satisfied, if I have a node U and the label of U is just the union of the labels of its children, or if it's contained in there, then I just remove everything below U from the tree. And this is where I use my exclamation mark and I mark U. So I make my tree much smaller and then I just mark U. So the mark shows that we have removed the children basically. But note that then in the next transition in step 1, we will again get rid of the mark because that was step 1. These whole 6 steps are just for one transition from one Safra tree to another Safra tree. Okay, so here's an example. I know this was quite confusing, but let's go through the example now. So let's say that we have this favorite automaton of ours that we see over and over again, and we want to create these Safra trees over it. So first of all, we said that the starting state S0 is just the obvious Safra tree that has just the root, and in the root we only have the initial states, which here was only Q0, and the root is numbered 1. Okay, so let's start from this and let's see what we get if we want to transition with the letter A. So what happens if I'm at this state, at this tree, and what I see is a letter A? Well, let's just go through these steps. first we have to remove the marks, but we have no marks here, right? The second step is that if there is a target, you have to put it in a child, but Q0 is not a target, only Q1 is a target. Then you have to actually do the transition. So with Q0 and A, as you see, you can only go to Q0, so it doesn't change anything here. Then there was this whole business of if you have something that appears here and also in one of the siblings, if you have other kind of things, if you have an empty set, if the label of a vertex is not a strict superset and so on, and these do not apply here because we only have one vertex. So all of these steps will be just skipped, and the transition from S0 with letter A would be to S0 itself. Okay. Now let's see what happens if you are again at S0 and I read the letter B. So the first step was to remove the marks. We don't have any marks. The second step was if you have any targets, create a child for them, and there is no target here because the only target is Q1. The third step was to actually do the transitions based on the original automaton. And here I can see that from Q0 with B, I can transition to Q0 or to Q1. So I update this set here and I make it Q0, Q1. Okay. And then we had this other steps which will also be skipped here. So if I start from Safra tree 0 from this one and read letter B, I will go to Safra tree 1, which is this one. But now I have a problem, right? Because I have, well, I know all transitions out of S0, but one of them led to S1. So now I have to know all transitions out of S1. Okay, so let's do this. Let's say that I am at state S1. So this whole thing is my state. And I've read the letter A. Okay, what happens? So the first step was remove the marks. There are no marks. The second step was if you have any targets here, create a child. And there is actually a target Q1. So I create a child for this vertex and I only put Q1 in there. And well, this child gets a new number, of course. So this is vertex number 2. Okay. The third step was that we actually apply the transition. So my letter is A and I'm starting from either Q0 or Q1. So here from Q0 with A, I can go to Q0. With Q1 and A, I cannot go anywhere. So this set gets updated to just Q0. And here I have only Q1. My letter is A. So with Q1 and A, I cannot go anywhere. So this set gets updated to the empty set. Okay. Now, the next step was you remove the empty sets. So you just remove this and you get this, which is the same as S0. Okay. So the transition from S1 with letter A would give us S0. What happens with letter B? So let's say that I start at S1, which is this state, and the letter that I'm reading is B. Okay. So again, the first step was if you have a target, you give those target states a new vertex. So there is Q1 here, which is a target. So it gets its own vertex and the vertex gets a number. The next step was you actually apply the transition. So again, from Q0 and Q1, reading B. From Q0 reading B, I can go to Q0. From Q1 reading B to Q1. So this gets updated to itself. And what if I'm in Q1 and I read B? Well, again, I can only remain in Q1. So this becomes Q1. And then we have the other things like if you have empty sets and things like that, but that doesn't happen. So this is our final Safra tree in this case. So if you start with this state, with this Safra tree, and you read the letter B, you will end up in this Safra tree. Okay. Now you see the problem. We now have another Safra tree, and we have to now define the transitions out of this one, because each one of these are going to be states in my final deterministic Rabin automata, right? Okay, so what happens if I start from S2 and read the letter A? Okay, this is my starting state. So the first step was, if in any of the labels you have a target state, you will create a new child for that target state. So in the label for 1, you have Q1, you create a new child. This becomes vertex number 3. But also in the label for 2, you have Q1, so you create another child, this time for 2, and this becomes vertex number 4. Okay, we did this. Now, what was the next step? The next step was actually doing the transitions. So with letter A, if I do the transitions, this is what happens. And then I know that I can remove the empty sets. So in this case, I go back to S0. Okay, we still have to go on with this example, but this is the last one, really. Okay, what happens if I'm at state S2 and I read B? Again, the first step was figure out if you have any target states and create new children for those target states. So I have Q1 here, I create this child, which has Q1 in it and gets a new number. I also have Q1 here, so I create this child. Okay, the next step was you actually do the transition. Okay, so if I start from Q0, Q1, and I have B, where can I go? I can go to either Q0 or Q1, so this doesn't change. If I start with Q1 and I do B, I can only go to Q1, so I just remain where I was. The transitions don't change my Safra tree in this case. Okay, the next thing that we do was that we looked at vertices that are siblings, and if there is a state that appears in several siblings, we only keep the leftmost one. So here, Q1 appears in both 2 and 3. So we remove it from 3, and 3 becomes the empty set. Okay. Finally, the thing that we did was that if there was a vertex where the label of this vertex was not a strict superset of the label of the union of labels of its children, we would remove its children, right? So here I have this vertex 2. Its label is Q1, but the union of labels of its children is also Q1. It is a superset, but it's not a strict superset. So I just remove this and I put this exclamation mark right next to 2. So this is the transition. Basically, we get this Safra tree, which we call S3. And so the transition from S2 with letter B would be to this S3. I don't know why there's a typo here. Okay. So you can continue this construction and work with what happens with S3, and you will see that with A, it goes back to S0, with B, it goes to S3. So this is the deterministic automaton that we get. And as you see, every state of our automaton is actually a Safra tree. So I had 4 different Safra trees, S0, S1, S2, and S3, and this is the automaton that they get. Okay, but of course, when I talk about the Rabin automaton, I don't only care about the structure, I also care about the acceptance condition, right? So what are those pairs of sets of states that I use as my acceptance condition? And this is how Safra defines them, and it's actually a very clever definition. So remember the vertex numbers that we had here, right? So in every Safra tree, there were a bunch of vertex numbers. And what it does is says, okay, so let's, for every possible vertex number, for every V in V, let's define a pair. And the pair that we define is as follows. So E of V is the set of all Safra trees that do not contain this specific vertex number V. And f of v is the set of Safra trees that contain this vertex, and also in which this vertex is marked with an exclamation mark. Okay. So in other words, if I have a run of my automaton B, which is the deterministic Rabin automaton, and that run is, for example, S prime 0, S prime 1, so on. This run will be accepted if and only if there is at least one vertex V, and this is not a vertex here, it's a vertex in the Safra trees. If there is a vertex V such that from some point onwards, this vertex always appears in my Safra tree, so I wouldn't remove it. And also it is marked with an exclamation mark infinitely many times. So this is basically our construction. So in this example, if you look at vertices that actually appear in our final Safra trees, there are only 1 and 2. So vertex 1 appears in all of our Safra trees. So the set of Safra trees that do not contain 1 is empty. And vertex 1 is also never marked with an exclamation mark. So the set of Safra trees where they have 1 and have an exclamation mark is also empty. But if you compute it for vertex 2, you get this. So our deterministic Rabin automaton is this automaton, and the pair is this. So what does this mean? It means that it accepts runs that visit S3 infinitely many times and visit S0 and S1 only finitely many times. So let's see what kind of runs do that here. So these are the runs that go to S3 and then just see a B and remain in S3 forever, right? So these are exactly the runs with finitely many A's, which was this, the words with finitely many A's, which was the exact same thing as the language of our initial automata. Okay, so at this point, this really sounds like magic, but why does this work in the general case? Okay, so let's prove that this is actually a correct construction. So we have 2 different automata. We have A, which was our initial automaton, and B, which is our output automaton, and we want to show that their languages are the same. Well, obviously, we start by showing that the language of B is a subset of the language of A, and then we prove that the language of A is a subset of the language of B. Okay, let's do the first one. I want to prove that the language of B, the language of my final automaton, is a subset of the language of my initial automaton A. Okay, so let's just take one word in the language of my automaton B, and let's show that this word W is also in the language of A. Okay. Because B is deterministic, I have a unique run on this word W. And because W was in the language of B, I know that this unique run is an accepting run. So let's call this run R0, R1, blah, blah, and these RIs are each a Safra tree, right? Okay, by definition, because of the way that I defined my sets of E and F, the fact that this run is accepting means that there is some vertex V, some Safra vertex V, and some index N, such that if you only look at this path from index N onwards, all of your Safra trees contain the vertex V, right? And also this vertex V is marked with an exclamation mark in infinitely many of these Safra trees that you see from index N onwards. This is just the definition. Okay. So because I have infinitely many of these indices where V appears, let's just give them a name. Let's say that these indices are M1, M2, and so on. So M1, M2, etc. are the indices where this vertex V appears, right? And now I can also look at the labels of this vertex because, well, when we were creating these Safra trees, there were many cases where we kept the number, but actually changed the label, the set that was inside this vertex, right? So it makes sense to say, look at the sets, look at the labels. that we had in the infinitely many times that we saw vertex V marked. Okay. And finally, let's actually chop our word based on these indices. So my first index was M1. So my first chop would be W1, which is from the beginning of my word up until index M1. Right? And then WI is from index I, from index MI to index MI plus 1. So now this is what I claim. I claim that my ICE labeling actually covers my I plus first labeling using the word that was between the ICE index and the I plus first index. This is also a type of distributed one. Okay, so what am I saying? Let's again look at what these indices MIs were. So MI was the index where we saw a Safra tree that contained that vertex V and also contained an exclamation mark next to V, right? So I'm looking at all those indices. And I'm looking at the labels of this vertex at those indices. Okay, so let's say that I'm at the ICE index that this has happened. So I have a Safra tree. This Safra tree has the vertex V, and the vertex V is marked with an exclamation. So what happens if I take one more step? When I take one more step, the first thing that happens is that the exclamation mark is lost, right? Because we always remove the exclamation marks first. So the exclamation mark is lost as soon as I take one step. But when does it come back? It comes back when in this vertex I have a bunch of children and the labels of these children cover the label of the current vertex, right? And for that to happen, what else should happen? I have to create those children actually, because right now there are no children. And in order for those children to be created, I have to actually see target states, right? So every time I create a child vertex, I'm just putting the current target states that I'm seeing into that child state. So basically, if I start from a situation where I have an exclamation mark right next to V, and if I continue until I see another exclamation mark, this means that on the way, in all of the possible ways that I could go this, like for each one of these vertices that are now in my label in Li plus 1, I had a path that visited the target states. This is exactly the definition that I gave you at the very beginning of this session. So for every for every state that is in the label of vertex V at the I plus first time, I know that there was one in Li that I could use this word and from there get to the point here, right? So going back, this is exactly this definition, except that instead of X, I have Li, and instead of Y, I have Li plus 1, right? At the beginning of this session, I showed you that if I can chop my path like this, then it should be accepted. And this is exactly what's happening here. So this path can be chopped at all the indices where we see vertex V with an exclamation mark. So in other words, what I'm saying is that the first time that I see vertex V with an exclamation mark, I know that I have seen my target states at least once. The second time that I see it, I know that I have seen my target states at least twice, and so on. And because this is an accepting run, I know that I see this state infinitely many times. So I have seen my target states in the original automaton infinitely many times as well. So this proves that the language of P is a subset of the language of A. Now let's do the other side. Let's prove that the language of A is a subset of the language of P. I'm going to run out of time on this one, but let's do it anyway. Okay, so again, let's say that I have a word W that is in the language of A. Now, because A was non-deterministic, I can have many different runs on W. But there is at least one of them that was an accepting run. So I take one of the accepting runs. Let's call that Q1, Q2, etc. This is the accepting run of A on W. And also I know that the same word W has a unique run here in B, because this was a deterministic automaton. So what I want to show is that this run is also accepting. Okay. So again, by definition, what I have to show is that there exists some Safra vertex V and some index N, such that all of my trees from index N onwards have this vertex V. And also the vertex V gets this exclamation mark infinitely many times, right? Okay, and the idea is actually really simple, and this is the nicest thing that Safra did. So try vertex 1, try the root of your Safra tree, okay? The root is never removed. So as you do your runs and you create new Safra trees, you are always sure that vertex 1 is always there. So it definitely satisfies condition A here. Now, if vertex 1 gets marked infinitely many times, then the problem is solved, because then it also satisfies condition B, right? So the only case that we have to solve is the case where vertex 1 does not satisfy condition B. This means that vertex 1 was marked only finitely many times. And because vertex 1 was marked only finitely many times, there is an index, which I call it M, such that vertex 1 is not marked any time after M. So vertex 1 is not marked in Rm, Rm plus 1, etc. Right? But then this run was an accepting run in the original automaton. So it means that there was some accepting state T that appeared both in the set of accepting states and also in this run infinitely many times. So let's take one of these states. Let's take one of these T's. Well, this T appeared in the run infinitely many times. So it also appears after index M. So I take its first appearance after index M and call that Qi. So let Qi be the first appearance of my target vertex T after index M. Okay. Now, what can I say? So this should have been Ri to Ri plus 1. So Qi, which is the same as T, was a target state. And I reached it at index I. So what do I have in my root, the root of my Safra tree at index I? I have all vertices that are reachable after I steps. So I definitely have T in there because T was reachable after I states. But what do I do based on my construction? Based on my construction, because T is a target state, I will create a child for vertex 1, and I will put T and all other target states into that child. Right? So in the transition from Ri to Ri plus 1, vertex 1 of the Safra tree gets a new child, and this child includes T in it. Okay. Now, when I add children, I always add them as the rightmost child of their parents, right? But as things go on, we saw that sometimes vertices are removed from the rightmost child and instead go left, basically, right? So I look at what happens to this vertex T. It might remain in this rightmost child that it was put at the beginning, or it might get removed. But if it gets removed, then we know that it exists somewhere to the left in one of the siblings to the left. And this can happen many times. It can basically move left, left, left. But it can't happen infinitely many times because the vertex 1 has finitely many children. So T can only move left finitely many times. So what this means is that at some point, we won't have any horizontal merging on T anymore. There is some point in time, for example, after, let's call it alpha 1 steps, where T stops moving to the left and just stays at one child from this point onwards. And let's call this child X1. So let's see what happened. Let's only look at the run from this point onwards. Let's only look at the run from the index alpha 1. So we know that X1 appears in every tree that we see from this point of the run onwards. Why? Because we know that T appears infinitely many times, and because, well, T is in X1, right? And we know that X1 is not going, and T is not going to move left from X1. So X1 appears in every tree that comes from this point onwards. And we know that vertex X1 will not be removed. Why? Because we had this assumption that we are already past the point where vertex 1 could get exclamation points, right? So X1 will only be removed if its parent gets marked, and the parent is not getting marked. So X1 will not be removed. X1 is going to be here forever. So what happened? The thing that happened is that X1 now satisfies our condition A. And again, I can just repeat this whole process. If X1 satisfies condition B, then I'm done. If X1 does not satisfy condition B, I can do all of this again and now find a child of X1 that has the same situation. But I can't do this forever. Why? Because my Safra tree is finite. So there is at the end one point where I can't do this anymore, and then condition B is satisfied. And so I proved that the word W is also in the language of B. So language of A is a subset of the language of B. Okay, this was the proof. And so let me finish by just giving you some take-home points. The first point that I really want you to remember is that a non-deterministic Boole automaton can be converted to an equivalent deterministic Rabin automaton. And actually, if you go back into this algorithm and look into it, you will see that if the original automaton has n nodes, then your deterministic automaton will have 2 to the power of n log n nodes. So this is like a factor of log n more than the finite case. And a very similar result, but much more complicated, exists for translating non-deterministic Boole to deterministic parity. And this is also a very celebrated result. It was obtained by Nir Peterman and published in Leaks 2006. So we have this kind of translation between the different types of automaton. If you have a deterministic Boole automaton, well, it's trivially also a non-deterministic Boole automaton, right? Deterministic is a special case of non-deterministic. What we saw here today was the reduction of Safra from non-deterministic Boole to deterministic Rabin. There is also the reduction of Peterman from non-deterministic Boole to deterministic parity. And there are a bunch of trivial reductions from deterministic to non-deterministic of the same type. So deterministic parity to non-deterministic parity. And I've shown this with green here. And there are a bunch of not exactly trivial, but not hard ones that I've shown in red. So for example, going from deterministic parity to deterministic Rabin, or going from non-deterministic parity to non-deterministic Rabin and non-deterministic Boole. And these are the homeworks that I want you to do. So I'm going to ask you for 4 reductions. And this is by the end of this month. So from deterministic parity to deterministic Rabin. from non-deterministic parity to non-deterministic Buki, from non-deterministic parity to non-deterministic Rabin, from non-deterministic Rabin to non-deterministic Buki. And when you do these reductions, what this graph shows us is that except for deterministic Buki, which was not as expressive as the rest of them, all of these are equivalent. They all have the same set of languages that they can model. Okay, and this is the end of this session. Sorry for going 8 minutes over time. Are there any questions? Sure.
What's the question? Why does the portrait finite?
Oh, why is it finite? That's actually a really nice question. So let's go back to the definition. So you see, each node of the Safra tree is labeled by a subset of the states of the original automaton, right? And also the label of each node is a strict superset of the union of the labels of its children. So each node has at least one state that is appearing here for the first time. So not only it's finite, it has at most n different vertices, where n is the number of states in your automaton.
So at most.
No, at most n, exactly n. Right? Because, well, take a leaf, it cannot be empty, right? So the leaf is introducing one of the nodes of the original automaton. Now take its parent. That parent is also introducing something new that wasn't already in that leaf, or any of its siblings. And then just go on. So you have at most n vertices.
I mean, the total number of Safra trees at most the square of the power of n.
Total number of Safra trees is a harder problem, but it's also finite because, well, we just showed that they have at most n vertices, so the number of trees on n vertices is finite.
Another problem is that how can we transform one model that's two different Safra trees? The only difference is that some the mark.
Well, I mean, it gets multiplied by 2 to the n in the worst case, right? Because you just take a tree and it's either has the mark at every vertex or not. So it's 2 to the n in different cases. So I think the total number of Safra trees was something like 12 times n to the power of n times something.